It's my first time at CppCon. I've thought about going for a lot of years and now kind of regretting that I didn't go sooner.
Hello, everyone. Let's get started. So my name is Danila. Today I'm going to talk about the long journey of changing standard sort implementation at scale. So who am I? I'm a senior software engineer at Google. I work on software efficiency for all our data centers at Google. So if you want to talk about performance, come to me. We'll have a lovely chat. So what's the agenda for today? Today we're going to talk a little bit about the history of sorting, like how it was developed in the standard library, what's out there, and the research behind it. So why have we decided to change anything at Google? A lot of bugs, so you'll love them. Implementation, which implementation we decided to choose, why, with pros and cons, efficiencies and inefficiencies. So, and last but not least, what can you do to improve your sortings, to improve, or maybe just to update the library. All right, so a couple reminders. So I believe if you wrote C++ for about a week, maybe a month, you wanted to sort some elements, and the sorting is pretty much just the ordering of elements. Today I'm going to talk about the calls, the calls std sort, stable sort, range sort, and similar partial sort, nth element, so all this stuff. So you can see that they might accept 2 or 3 arguments, 2 arguments like for begin and end, and the third argument, a user-defined comparator. That's a quite important detail, which we're going to talk later. So this is where most interesting stuff comes from. All right. Many of you should know what quicksort is, but just short reminder. So quicksort is a type of sorting, general sorting. So pretty much you take any element, all those who are less than this element go to the left, those who are more to the right, and then you recurse on both parts. And you can have different strategies for taking this element, maybe a median of 3, maybe just the middle one, maybe, I don't know, something out of some set. It doesn't really matter. Quicksort is the general description of any of such algorithm. And if we're gonna look at first STL version by Stepanov and Lee, we're gonna see these 4 or 5 lines. So third line is quicksort loop, and then final insertion sort. So how does quicksort loop look like? It looks like the strategy for partitioning. It takes median of 3 elements, and then it does partitioning, again, less to the left, more to the right, and it does some thresholding. So what does it mean? It means that if you have in the range more than these elements, just do as usual quicksort. If you don't have more than these elements, don't do anything, and the range will be unsorted. STL threshold in the first implementation was set to 16, because you don't want to go a lot of deep and deep. You don't want to have deep recursion. And when you have 16 elements, you're going to go 4 times. So other sorts might be useful in this case. Final insertion sort pretty much just smoothes out these inaccuracies for 16 elements. It just does insertion sort for 16 elements. Insertion sort is a type of sorting where you just go element by element and put it into the place where it should be sorted to the prefix. But it works quadratic time. So this is pretty much how it looks like the first sorting from first STL. You can see that you have more and more sorted range. And you see these little inaccuracies that for every 16 element that occur for every 16 elements. And in the end, it does this final insertion sort, and it just smoothes everything out. And now you have a complete sorted array. So this is kind of the first implementation of sorting that has been available in somewhat standard library of C++. Okay, but standard library evolved from STL. So STL is kind of a notion of standard template library. Now we call it just standard library of C++. And we have the following definitions for them. So the sorting can take 2 arguments, can take 3 arguments, and the only restriction that it should have like n log n comparisons. This actually hasn't been always the case. So for some time it was n log n comparisons on average, but in C++11 it was changed to have worst case scenario n log n. And quicksort, as you might know, but it's easy to understand, worst case scenario is squared because you can just pick the worst element and only eliminate in the recursion only 1 element, which is not great, but this is possible. So the initial quicksort no longer works as a standard compliant algorithm. So what has been done? And GCC libc C++ as well as LLVM libc C++, but that's in a couple slides, introduced a notion called intrasort. What does intrasort mean? So this is the intrasort loop, and you can see final insertion sort is still there, so it hasn't gone anywhere. But like in this and you can, the difference is only in these calls, and intrasort loop has on line 8 this argument. So it has argument of 2 times logarithm, it's like base 2 of last minus first. So what does it mean? So what does it actually do? So this algorithm is called intrasort. I have no idea when it was named like that, but whatever. So it's almost like a quicksort, as you can see. It has the same, almost the same arguments. And if we suspect a lot of recursion calls, so for example, I don't know, we don't want to go quadratic, otherwise like you will exhaust your stack. So in this case, just use heap sort. And this argument actually is what just limits the number of layers you go deep into the recursion. Microsoft standard library does pretty much the same, but with the only difference that when it comes to 16 elements in the range, it just calls insertion sort, whereas GCC libc C++ calls insertion sort at the end. Like the GCC version might be a little bit faster because if you do like linear accesses, you might get better cache locality, which might result in better efficiency of performance of standard sort. All right, but if we think a little bit like about the worst case scenario, like it's just not great. I mean, it still does the job, but it does it like slower. And you can see that performance of sorting can vary from input to input. That's usual in this area, this research. So, and you can see in the end, it also tries to smooth everything out. All right. Today I'm going to talk a lot about LLVM libc C++, because at Google we use it primarily for pretty much everything that we built. All products, all that are written in C++ are built with standard library from LLVM. But they didn't do a lot for, like, they didn't do anything for a long time. So in 2014, the issue was reported that standard sort has worst case, quadratic worst case, but standard mandates n log n. However, like, it took only 7 years kind of to fix it. So what's wrong? Like, first of all, why was that? The answer is just simple. Actually, anybody of you could do and just implement that. The thing was, nobody really cared a lot, and like that's the only factor. And after that, we implemented that. We found that only 0.01% of calls got into this heap sort fallback in production. So yeah, this is, I mean, Google production might be biased, of course, but that's what we've seen so far. So if we talk a little bit about LLVM history and sorting in LLVM history, it doesn't do only quicksort. It didn't want to do only quicksort. It only wants to be a little bit faster than libc C++ back then. This is the slide from LLVM conference from 2010, I guess. C++11 hasn't been adopted. And what it wanted to do, it just wanted to adapt to to certain patterns. For example, equal patterns, ascending, descending, even odd, some pipes, like maybe almost sorted, and random, of course. Random sorts are also important. And as you can see, LLVM libc C++ really worked well on these patterns, and the truth is, such patterns are actually quite, they are not rare. They do exist a lot, especially in sorts that are not big. For example, I know 100 elements. Like a lot of cases we've seen where it was sorting almost already sorted array. And like here comes the question, a very good question that we want to kind of like answer before we do anything with the implementation. What does constitute a good sort? What is a good sort? So first of all, it should like to have n log n comparisons. That's that's written in the standard. Probably it wants to recognize sorted patterns. We don't want to sort a lot of random. We don't want to waste a lot of time on already sorted arrays. It should be kind of fast for modern hardware, and fewer comparisons for heavy sorting, for heavy comparison sorting. So assume you have sorting comparator, which reads from chunks of data for like SQL database, and the fewer comparisons you do, the fewer reads you do. The hardest part of all that is actually the third bullet, because hardware changes and we need to change the implementation as well. But how are we going to change it? So is it okay just to change std sort? I mean, on one hand, yes, it's good, but let's see first of all why do we need other patterns as well? So libc++ on ascending input already finished, and you can see libc.c++ on ascending does some weird stuff, which I know hasn't finished yet, but we'll just wait and see how it sorts the elements. All right, now it finished. So patterns are important, hardware is important, and log n comparisons is important. So what can we do about it? Patterns, first of all. I want to talk a little bit about how libc++ has achieved that. And what it does, when it tries to recurse on subarrays into quicksort, what it does a little bit of insertion sort. But insertion sort up to the end will be quite bad. It will be quadratic in the worst case. So what it does, it just sets the limit. So it tries to insert at most 8 elements. So it just goes, sees, okay, this is the sorted prefix. Oh, this is the element that's not in this place. Let me move it. And only do such operations 8 times. So find 8 elements at most, which are not sorted, and put them to the right place. Once you put them into the right place, you can recurse on the part that is not sorted, and everything will be really nice and sorted at the end. And in the way, for example, it recognizes ascending patterns, like patterns where like almost everything is sorted, and it's good. Yeah, for sorting and hardware, the story is somewhat interesting because every now and then, and actually research has started, like research for sorting has started, I don't know, since 1950s and continues even now. And you can see a lot of stuff has been done. For example, I don't know, x86 CMD sort, VQ sort, vectorized, portable quick sort. Somebody wrote a faster sorting algorithm. Somebody said, okay, pattern defeating sort is better. Boost library has 4 different sorts. Like, what should we do? Like, which sort should we choose, and why? The answer is we probably, as C++ programmers, should choose the default call to std sort. And the question then, okay, can we change it to something faster? Because I mean, 10 years have passed. Can we change it to something faster? Yes, and our main motivation was to save cycles. One more motivation was that we've seen some production failures, but that's like a little bit later. So we tried. I love working at Google because we have hundreds of millions lines of code, and I just can I just can change something and just see how it fails. And it failed quite a lot. So let's look at this picture a little bit longer than for other slides. This is pretty simple. Don't read too much. In the middle, you have like a simple SQL script which inserts some ID1 and which inserts ID1 and ID2 tuples into the table. And then what it does, it just selects everything from this table, order by only first column. And you can see on the left, Postgres just outputted, has the output which is different from MySQL. And why is that? The truth is we just ordered by the first element, and second element doesn't promise any order when you have ties. And we call this problem ties. And we had a lot of these problems. Let's look at some C++ code. Say you have a pair of vectors, and you want to sort, say, I don't know, by first element. And if first elements are equal, then the order of the second element is not defined, because this sort, like standard sort, is unstable sort. It doesn't promise any ordering of equal elements. And a lot of people wrote tests which pretty much said, okay, do something, it does some sort in the middle of the function, and then expect some, I don't know, prod above JSON, some golden test. And this actually caused a lot of pain when we tried to change the implementation. Yes, and we decided, okay, in order to change std sort to something better, and at the same time we're going to improve testing, because people who depend on golden tests probably don't do real good job in what they really test. Anytime we're going to change anything, they're going to be broken, and we wanted to find such cases, we wanted to fix them, we wanted to make them more robust. So how can you do that? The answer is pretty simple. Just do the randomization. So this is the randomization which we added before sorting. So just randomize elements and then do your usual sort. We decided not to include that in like optimized builds. That's on the macro. However, like we included this macro and find a lot of cases, a lot of flaky tests, a lot of problematic golden tests, how can we do that actually in the standard library? Because funnily enough, in the standard library, when you want to do something, just I know some shuffle, you need to depend on the header random. And header random probably depends on header algorithm because it needs std min, std max element, and something like that. We use technique so-called address space layout optimization. So you have, I don't know, a global variable which has its address. If it's loaded randomly into memory, it can be a good seeding. It can be a good seed for linear, I don't know, random generator. And it's by default on macOS. It can be turned like it's by default on shared libraries on Linux. So it was pretty good for us. All right. We thought a little bit about randomization. So you can randomize std sort before doing the actual sort. However, there are other calls that like deserve randomization as well. For example, std nth element and std partial sort. Std nth element is an algorithm which it has 3 arguments. First and third arguments are begin and the end of the range. And the second argument takes a iterator to something in the middle of this range. And it promises to order the elements in the way that this middle element is put into the array as if it was sorted. For partial sort, first elements up to this point, up to this iterator will be sorted, and you can see fun facts that nth element of begin plus 9 like has the element sorted only for partial sort, which has begin plus 10. So this plus minus 1 is actually very tricky, and we found a lot of bugs when we decided to randomize the ranges where the order is undefined. And for example, for nth element, the order of both parts are undefined. So anything can be there. Nobody should rely on that. If we want to, implement a new algorithm for nth element, like that should not be relied on. For partial sort, pretty much the same. The right part has a property that the order is undefined. So how could you do that? Pretty simple. Just randomize range for nth element, randomize range before, randomize a range that comes up to the nth element, and randomize range that comes after nth element, strictly after. For partial sort, these are 2 randomizations, just before and the right part. So bugs, probably the most interesting part, and honestly, I know maybe I did a couple bugs as well. First of all, determinism, golden tests, and for example, this is an example from ClickHouse which is written a lot of in C++. How was the test fixed? Pretty much they extended the ordering in some tests and moved the reference files here and there. We've seen a lot of failures in MySQL, in Postgres, so in MySQL, and we haven't seen failures in Postgres because it's mostly C. But yeah, a lot of other places as well inside Google. So harder cases involved more time. For example, assume you sort some data, you're a search, and you cache it somewhere. Then you have ties, and they're handled randomly. And now you have lower hit rate, cache hit rate, because ties can change something that's on the border where you want to, I don't know, limit the result. So you might have different data depending on different sorts, and your cache might invalidate. We couldn't afford that even if we change it only once, because assume you change only once, and then throughout the rollout, you will pretty much dunk your cache, which is not great for services. And we tried to find that. We were pretty successful in it. But these are harder cases for Goldens. Sometimes, yeah, in order to fix such Goldens, you need to use probably stable sort. Stable sort promises that the elements in which they were in the original array, equal elements, it promises that equal elements in the original array will be in the same order in the resulting array. So it's deterministic. And actually, I wondered why in my computer science course we talked a lot about like stable sorts, and the answer is this: you want like stable sorts if you want determinism. All right, other bugs. Let's try to write a median function. I mean, it's pretty good. So we just do nth element to the median. Just take the result of this median. Well, if there are even number of elements, we should take median from like -1 and like take the average of these two values. And the result will be just element in the vector from median and median -1 over 2. And we just return the result. Does anybody see the bug in this snippet? All right, quite a few hands. Okay. Yeah, the bug in this snippet is that you call nth element twice, and the second nth element might rewrite the element, for example, on the position med. Like v of medium might not be like the one that was here, because nth element doesn't specify any order on both parts. But you can get lucky, because nth element actually puts elements around nth close to total ordering. And let me show you examples from, I don't know, from GitHub repositories. So this is exactly what happened in some repository with 3,000 stars. This happened in repository for Matplot, I believe. It's a famous library for, I guess, Python, but I might be wrong. Matplotlib. So you can see they try to use to compute interquartile range, but they called nth element first, and then nth element second one, and then they access the elements in the array, and probably they have incorrect results. Another element. Actually, it's another bug. Actually, it's quite funny, because there is a snippet that this was taken from Geek Forces, and probably you know this site. And yeah, actually you can go now to Geek Forces, and there will be exactly this bug. Another bug. It's Ableton. Another bug, medical image analysis. That's scary. Another bug, and I can continue like infinitely. So what you can do, if you use LLVM libc++, please use this macro in your builds if you want to randomize randomized sortings, nth elements, partial sortings. It proved to be really useful in finding bugs, fighting golden tests, and like it improved the test, how people think about testing. So it's probably the most important part. All right, now let's talk a little bit more complicated stuff. In order to sort or do anything complicated with ordering in C++, your elements and your comparator should satisfy so-called strict weak ordering. What does it mean? It contains of 4 properties. So if you compare element with itself, the result is always false. Like it's very logical. Asymmetry, if one element is less than another, then the other way around cannot be true. So transitivity, if x is less than y is less than z, then x is less than z. And 4th property is a little bit more complicated, but it's still needed. What it means that the incomparable elements, like they considered equal among each other. So, for example, like if x is less than y is false and y is less than x is false as well, then we consider these elements equal. And if 2 elements are equal and another 2 elements are equal, then first and third should be also equal. Like interesting fact, and I've heard a lot, even from the standard library, from the people who implement standard library, that such checks are very expensive. So in order to check everything here, for example, for the third and fourth condition, you need kind of to traverse over triples of all elements in the array. And in order to validate that your input like satisfies strict weak ordering, we need like cubic time. That's completely inappropriate for analog n algorithm as STD sort. So, but let's think a little bit, but what are the risks? What if we don't do that? On paper, it's undefined behavior, but I'm more interested as an engineer what happens in practice. And in practice, I mean, best case scenario. Best case scenario, you can sort, and then STD is sorted, returns false. Well, not great, but at least it doesn't fail. Probably, yeah, but probably it's not great. Like, let's look at this example. Probably you see something. On the left, it's a very simple code. I just have a vector of integers, which is filled with -1, and then I sort them the way that to the left, I want all negative integers, and to the right, I want total ordering of positive integers. And at first, it seems an okay comparator, but if num-elms, if I put num-elms to 30, this just works fine. It just sorts and doesn't do anything, so that's okay. But if we put 31 elements, it actually fails with segmentation fault. And this is actually very tricky because, like, I can prove that with this comparator, there is no single case that when it fails with less or equal than 30 elements. And this is actually quite interesting because, okay, if you don't have in your range 30 elements, then all good. If you have more of them, something can fail. But I haven't written a well-thought test for 30 plus elements just to test sorting. And we found a lot of attack vectors in this area. So if you have incorrect comparator, then I can fail your sort with 31 elements, like with out-of-bounds read, pretty much. So, and this is also one reason why we decided to change anything, because at Google, like once in several months, we found some problems, like literally production failures, out-of-bounds reads, segmentation faults, scary stuff, attack vectors, security is like doesn't work, and all that stuff. We were scared, like weeks of debugging, all that stuff. And yeah, why does it actually why is it even happening? The truth is, when you do the partitioning in your quicksort, you kind of wait for an element to be false, because, for example, if you start with a pivot and then you go further, at some point will find that there is a pivot element, and you compare pivot with pivot, and this should result in false. And this while loop should end. But if it returns a lot of trues, then it doesn't end, and then reads out of bounds. One solution, of course, is just to have a bound check here, which we'll discuss a little later. However, well, if you know that your comparator is correct, you probably don't even think, oh yeah, I'll definitely find an element which is less than pivot, which is not less than pivot. Yeah. So, but still, the risks are actually quite huge. So we have failing production, we have incorrect sortings, but still the check actually is cubic. What can we do? First thing, we use some maths to reduce the complexity of such check. I'm not going to dive into why it works. I'm just going to tell you the algorithm, how it works. So first of all, we need to sort the range with some algorithm that doesn't fail. This is a little bit harder than you might think, but just, yeah, imagine any algorithm that just finishes and correctly sorts when the comparator satisfies strict weak ordering. Just sort the range. If it's not sorted, return false. If it's not sorted after you sort it, then your comparator does not satisfy strict weak ordering. Then find the prefix of all equal elements. So just compare your first element with the next one, and until you find something that's bigger. Check that these elements are equal among each other. Check that they are less than all that remain, and just remove them. It's a little bit not very obvious why it works. You can read the proof by the link above. But it works. So still, we have a squared algorithm for checking strict weak ordering. And what we decided to do in the end is, okay, we have a sort. We have a quadratic algorithm that kind of tells you, like an oracle, does your comparator satisfy strict weak ordering? Or maybe it's not. Maybe it does not. And we decided to try out, okay, let's check just first 100 elements. Surprisingly, it worked insanely well, because most sorts are small. Majority of cases are sorts under 100 elements. Having, I don't know, 10,000 comparisons, extra comparisons in debug builds, hasn't resulted in any timeout across all tests that we had at Google. And yeah, we were very happy actually to discover that limiting this check works and finds most issues. For a cubic algorithm, we thought about 20 elements, because if you have 100 elements for a cubic algorithm, that's going to result in around 1 million comparisons, which is probably a little bit harder to do. So quadratic algorithm allowed us to do it on 100 elements. All right, but there are some caveats to this algorithm. So first of all, the sorting should not fail, but we've seen that you can give invalid comparator some input, just reads out of bounds. It only tells that the strict ordering is met or not. It doesn't give you the triple. There is no algorithm to give you a triple, no quadratic algorithm which gives you the triple that violates a strict weak ordering. And arbitrary comparator can do anything. So sorting can fail, for example. Comparator can fail if you give it, I don't know, 2 elements, second and 98th element. And probably in your sorting you never call that, but we might. Third bullet was not very relevant. We haven't seen many of such cases. The hardest was the first one. So what we decided to do, we decided to extend the debug builds. So one thing to kind of fight out-of-bound reads is to do ASAN builds, address sanitizer builds, debug builds, to find most cases, or to have another oracle which can point you to some problems in your program. And yeah, we decided to go with this request. We decided to go with this proposal to LLVM community. It was accepted pretty fast. So first thing we did is just out-of-bounds check in cases where we partition the elements in quicksort. That just gives us the opportunity to find, if it fails in, for example, on line 510, then your comparator is not strict weak ordering. Then we enabled strict weak ordering checks for stable partial STD sort, and it was rolled out in LLVM 17, which release was probably a week ago. And if you use LLVM and libc++, you can use these command line flags to enable strict weak ordering check in your projects. All right. At Google, it took us around 6 to 7 months to fix everything. I wouldn't say that we worked like full time on fixing everything. It was just more like a thing that, like, hey, I had 20 spare minutes. We have a thing called, it's a collaborative project, so you can kind of jump in, fix a couple targets, and move on with your project. So some community contribution. And yeah, but it took us overall 6 to 7 months to fix, to find issues. We found fewer of them, but they were much scarier. So I'm going to list not the actual bugs, but the families of bugs. So first bug is when people tried, okay, I have STD less, I'm just returning left-hand side less than right-hand side. Oh, if I want to sort in the other order, what I do is just I need to negate it. No, unfortunately not. You cannot do that because irreflexivity would not be met. A more complicated bug in this case looked like that. So you were reading a flag. Do you want to sort descending or ascending? And bug was only happening when the descending is false. But when it was true, everything worked fine. Another issue, if you have one element in your vector, no comparator is called, because why would you? One element is already a sorted vector. Like a vector of one element is already a sorted vector. But if you have a comparator which dereferences some pointer, and you have you have an element which doesn't have any value, and dereferencing is just null, then you're dereferencing a null pointer, and that just results in a failure. Another thing was another failure was to check if something doesn't have any value and just to partition it. I do have some elements which I want to partition to the left, but they don't have any value. And those who do have value, they will be ordered by their operator less. This is also not correct, and because comparator of the same element can be true. And this is exactly the thing that I showed you in Godbolt, where I can give you 31 elements and your sorting would read out of bounds. The correct fix here is to swap first if with the second if. Then it's a correct comparator. Another bug, another family of bugs was people treated ties differently from how they compared it. So in this case, they computed something from the element, some difference between days, and then they returned absolute value with these differences. And you can construct example which fails such sort, which is also not great. Assume you are Google Drive and you compute something what should be deleted first, and you delete in incorrect order, which is probably not great. Another family of bugs was that, they were comparators with thousands of lines of code, and they were writing these comparisons, and they were good, and then in the end, they just return true. No, unfortunately, that's not also correct. You need to return false when you have completely equal elements. Another family of bugs was developers wanted to compare some elements, and sometimes the comparison just doesn't result in a correct, I would say, it cannot compare it because, something has gone wrong. I don't know, the networking issue or something like that. And what they decided to do is, if we cannot compare anything, let's just return false. Unfortunately, that's also exploitable. That doesn't work, and you need other mechanisms to kind of understand what can go wrong. Maybe throw an exception from here. Maybe do something else. Another bug, which is might be less obvious to people, that sometimes you want to, okay, I want to sort some floats, but I want to, like, some floats should be equal. I mean, I don't know, I did some ranking, and if the epsilon comparison results in true, these are probably, like, they have the same ranking. So I would just return by ID. However, this is not a correct sorting, because in this almost equals, they do compare floating numbers by some epsilon. And A can be equal to A plus epsilon. A plus epsilon can be equal to A plus 2 epsilon. But A is not equal to A plus 2 epsilon, because 2 epsilon might be more than they compare their floats. And this results just in incorrect sortings. And unfortunately, transitivity of incomparability is lost here. And this is actually probably the bug that we face the most. So a lot of developers thought that it's okay to, I mean, it's generally a good rule to compare floats by epsilon. So you don't want to say, okay, this less than this by just looking at their like mantissa and exponent. However, yeah, in sorting, it might result in something bad. Another issue which probably, I don't know, happens from time to time on Hacker News or whatever. If you sort the vector of floats, it can be undefined behavior. Why? Floating numbers can be none, not a number. Not a number, numbers by IEEE 754. This is a very scary name for me, but doesn't matter. It always returns false. So x is less than none, returns false. None is less than x, returns false. By incomparability, it means that x is equal to none. And it means that every element is equal to none, but not all elements are equal among each other. So it means that if you have nones in your container which you want to sort, unfortunately, it might result in incorrect sorting. This is a very funny bug. This is another funny bug. So we found that, so on the left, you have a vector of floats, and you want to sort from begin to end, but with a greater, and you made a bug, integers. And on the right, I put -w everything, so give me all warnings that you have, and doesn't give you any warning. So you want to sort vector of floats with greater comparator. However, you might misspell float, you might forget this is a vector of floats, or actually you might want to change the type of vector of float, and nothing will give you a warning. So even though C++ is a type-safe language, sometimes I wonder how such things even happen. A lot of bugs in open source as well. So this is some Android. Yeah, this is the bug of the case where if all elements are equal to CFA reg, then this might result in a failure. BFP trace, same bug, 5,000 stars. Another repository which just returns something less than equal for some reason, I don't know. Chromium WebRTC, also very interesting bug. You can exploit it, but it already has been fixed. So yeah, so as you can see, I could give more examples here, but I don't have much time. And let me talk about interesting stuff which you might never consider what you can do with your sortings. This is a snippet of code which might be hard to read, but you don't need to understand what gas means, or candidate, or num solid, whatever. All you can see that here that these elements are changed along the way of calling nth element or std sort. So this element is changed sometimes, and then you kind of order by it. So you can construct, I don't know, a comparator which self-modifies some array and returns sorting by giving you, I don't know, it just, let me put it this way. The algorithm gives you some elements which it wants to sort. And you can trick this algorithm, for example, in the worst case scenario. And this is the snippet where you can trick, I don't know, std sort or nth element to be the worst case scenario, always. This is somewhat artificial, I would say. You probably never write comparators which modify the array like along the sorting, but it's valid. It's okay. It satisfies strict weak ordering, and however, std nth element will always result in quadratic worst case for that. And there is an issue on GitHub which provided a little bit of like talks and comments, like is it actually valid? Do we need to fix anything? And nth element requires linear complexity on average. However, we have a comparator where every time you call the sort on any range, like it results in quadratic behavior because you kind of can trick nth element to be quadratic. That's also like a funny bug. It was discovered like long time ago. Pretty much in the case how you find problems, and how can you find problems in your quick sorts. So, all right, some sorting trivia. Can we sort 1.02, 1.01, 1.0? Probably yes. Yeah, I don't see any problems. All right, can we sort 3.0, none, and 4.0? I explained no. Because none thinks that it's equal to 3.0 and 4.0, and 3.0 is not equal to 4.0. Can we sort none, 3.0, and none? Surprisingly, the answer is yes, because all elements are equal, and there is no, 4.0, which is equal to 3.0. So even though your vector might have nones, you might get lucky, and you can sort this. If you have like nones and some other element which is equal to all other elements. So for example, if you add a couple 3.0s here, that's also going to be fine. All right, last section. What are we changing our sorting algorithm with? So we made cleanups that resolved all golden tests, fixed all bugs, most bugs on strict weak ordering, so now we are ready to change something. We decided to choose a mix of block quicksort and pattern defeating quicksort. Let me briefly talk about what they do. The necessity actually comes from the partitioning algorithm. And partitioning algorithm has these two while loops. These two while loops are data dependent. And branch predictor doesn't do a very good job on finding, on predicting these branches because, you have random data and it cannot predict anything. So we saw a lot of branch mispredictions in sorting. So what we decided to do, we decided to use a technique called block quicksort. So what we do, we just store the results in a bit set, pretty much in an integer of 64 bits from left and right. Then what we do, we just find with count trailing zeros, call the bits that need to be swapped. We lower the bits, these bits from 1 to 0. These are just one instructions on x86, and just swap these elements. This helped to reduce branches a lot. And another change that we decided to do, which is more relevant to pattern defeating quicksort, is so-called Takis neither. So when you want to find any element which partitions quicksort, it's called pivot. You take 9 elements, find the median in every 3, and find the median out of these 3 medians. That's called Takis neither. And this proved to be really good for random data and reduces the number of comparisons overall. This is Godbolt, which gives us that, block quicksort is really nicely vectorized when you compare a lot of integers. So which results do we have? On integers, on random integers, we have up to 50% results. On some other patterns like ascending, descending, we regress, but just by a bit. But still, when you are you have an ascending array, if you're sorted a nanosecond per element or 1.03 nanosecond per element, that's probably doesn't matter much. On more interesting benchmarks like strings, because strings cannot be vectorized properly, and you have pointer indirections from array to strings and so on, we have around 10% win. And all right, some thoughts. So we're heading towards the end, just a couple minutes more. C++ is a weird language in a way that our default sorting is unstable. Other languages like Python, Rust, and Java have stable default sorts. So if you call .sort in Python or Rust, it's just a stable sort. It doesn't have any problems with golden tests, and it has like specific like sort unstable calls. For C++, it's the other way around. It's std sort is stable, and you need to call stable sort kind of to stabilize things. Another interesting question is, why do you even implement some algorithms that can read out of bound? Why shouldn't we just be a little bit safer from the standard library standpoint? A good question. Probably we should. Fun fact, I heard a lot that rangers sort, and overall rangers wanted to have one argument a lot, like just container argument. Because if you have two arguments which take the begin and the end of the range, they might be from different containers, and there is no warning against that. So we found literally 0 bugs where we had different iterators in a standard, like in 2-argument standard sort. Maybe we're just lucky, maybe it's not, but I don't think that this argument for migrating from std sort to std ranger sort reduces a lot of bugs. C++ 20 allows us to make fewer bugs. We return from operator's spaceship the ordering that we need. It works much better. You don't need to write your own comparators, which might be buggy. So what are the results of all that? So overall, the whole effort we call a comparator sanitizer. So we find golden tests, we find broken comparators. It prevents from out-of-bound reads, prevents exploits. I believe it deserves a name of sanitizer. We saw in production around 7 to 8% improvement, not 50 as we've seen for random sorts. For random integer sorts, well, we expected a little bit more. Okay, I'll take 7-8% improvement in sorting. Reduced a lot of branch mispredictions. We gave this capacity, branch predictor capacity, to something else. Fixed literally thousands of bugs. For the Hiram's law, like my take of all that even simplest things are hard to do right. When I started this project 2 years ago, I thought, I would finish that in 6 months. No, it took around 2.5 years, definitely not full time. I was like on and off of this project. This was fun to do. Okay, what can you do? Use these command line flags if you use libc++, because they enable you randomization checks and strict weak ordering checks. Probably you can make randomization for other algorithms. Probably you want to make randomization for standard partition or std make heap. I was a little bit lazy to do that. Like you probably can do strict weak ordering checks for nth element. I didn't implement it for nth element because in the algorithm that in the quadratic algorithm that I described, you need to sort the range. Probably you don't want to sort the range to do nth element, but that might be okay for debug build. What can you do else? Remember, Bjarne today talked about invalidation of vector iterators. Well, I don't know. They can be ideas which were very successful for strict weak ordering checks. Let's just in debug build reallocate vector on first 100 pushbacks. We'll find a lot of bugs with dangling references, dangling iterators. Probably it will help a lot. These are the links that you can read. My blog where I described all this effort, LLVM request for comments, sort and change itself, Fabricator review in LLVM. Here are my details. If you want to get in touch, please do. That's it. I'm happy to take your questions. Yes, if you have questions, please go to the microphone.
Thank you. Was very interesting. I believe that the reason you don't see an issue with greater end is that libc++ disables warnings in standard library headers.
Yeah, probably you're right. Yeah, I know about that. Thank you.
Oh, I also have a suggestion for that. It's more of a comment. But instead of std greater int, use std greater that : element type.
Yeah, that also.
The type of the,
Yeah, that also works. But yeah. Well, finally enough. Second question about this weird bug. Okay.
Thank you for the great talk. You mentioned finding a lot of bugs regarding improper use. Did you ever find any attacks against Google infrastructure or Google code, kind of exploiting this DDoS or so on? Or
Okay, that's an interesting question. Even if I knew about something, I believe I wouldn't be allowed to talk about them.
okay.
So, but I don't think that I know about anything.
Thank you.
Have you looked at what happens if a stud map gets one of these bad comparators?
Also interesting question, thanks. This is actually my next kind of plan for this adventure. Let's try not only to get to the algorithms, but also like to containers. I believe for standard map, standard set, you might get weird results because, well, these are trees. These are red-black trees. And if you mess up with red-black trees, you might get, I don't know, linear trees or something like that. I might suspect that if you supply some comparator which is not great, it might result in something very long. So yeah, I do think you can exploit that right now as well. I guess there are no more questions. Thank you so much.